Hi, Brent.
Hey, Elysia.
Hi.
Hello, how are
Um,
you?
I'm doing okay. I mean, I'm not so overwhelmed. Okay, I'm still a little bit overwhelmed by the
Uh-huh.
mechanisms. But like, I guess like doing the practice that you gave me. Okay,
Yeah,
I'm
yeah.
not, I'm not admit I didn't do all of them, but I did most of them. I think I left only like two, either two or three undone, but I did most of them.
Yeah.
Um, yeah.
That's good. Were you able to do the mechanism as well, or did you just
Yeah,
predict the product?
no, I did the mechanism as well, which is kind of what took me a while, and um, yeah, I didn't get to do all of them because
Mm-hmm.
I actually did put the time for it. But let me see if I could send it to you.
Yeah. I
Um,
got yours, Layla, like your answer. So I'll be checking your guys' answers, Elysia and Layla's answer for the homework that I gave you guys last night.
Okay, thank you so much. I low-key had lab until like an hour ago, so I did it like 20 minutes afterwards. So I think I got a lot of them. Like I was confused.
Oh, shoot.
But
Are you
yeah.
at the library right now, or are you like back at your
No,
apartment or
I'm back
dorm?
at my house.
I see. Dang. Dang, you did it pretty quick.
Yeah. That's why I feel like I probably did it wrong.
It's
I
okay.
kind of
It's
just
okay.
like tried to do my best like thought process behind it without looking too much at the slides so that I could see what I know and don't know
Don't know, yeah, and
first.
then like study what you don't know later on. That's good.
Exactly, yeah.
Mm-hmm.
But that's why I think I low-key messed them up.
Yeah, we'll see. We'll see. Let's see here. Just gonna make sure. Carbenes, analysis, alkynes, bacterium, CH. Okay, yeah. So for this one, let me share my screen here. Okay. The first problem here is going to have us react this alkene with these three reagents, which you guys notice that is going to form cyclopropane ring, especially the first and third one. Where the second one with the chlorine here is going to attach chlorines in the middle of that cyclopropane ring right there, right? And yep, you guys had that correct. Nice, nice. I'm just looking at the mechanism. Yep, yep. Correct, correct. Yeah, so that's correct. Elisa, you got the stereochemistry right as well. Layla, for your answer, it would be more correct if you put the cyclopropane as having stereochemistry because the two chiral centers we formed are these chiral centers right here, one here and one here, right? So the cyclopropane ring, which is going to be from this bond to this bond, they're going to have either both wedge or both dash. So we could say plus minus here, right?
Why
And
would I
same,
have stereochem again?
yeah, it would have stereochem because we are forming two chiral centers. One chiral center over here and another chiral center over here. And whenever we form chiral centers, we always have to put wedges or dashes. And in this reaction here, it's syn addition, where we're adding the bonds on the same phase. Because if I look at the mechanism of the first one, let's say CH2N2, with this alkene, this is what it's going to look like right here. So I'm going to draw out the C out like that, and it's bonded to two hydrogens like this, bonded to this nitrogen, which is triple bonded to that nitrogen, and this carbon here has a pair of electrons negative charge, and this nitrogen here with 4 bonds will have a positive charge because it has 4 bonds. The overall charge would be 0 because those charges cancel out. Think of this N2 here as the best leaving group we have. That is going to just leave by itself, right? Think of it as an SN1E1 type mechanism. This leaving group is going to leave by itself, which is going to leave as N2 gas and have us form this carbene right here, right? And this carbene right here is what makes the cyclopropane. The formal charge of this carbon right here is going to be 0 because it's on the 4th column. It wants to have 4 electrons to itself. And we calculate how many electrons it has to itself. It will have 1, 2, 3, 4 electrons to itself. So 4 minus 4 is 0. Formal charge of 0. But this is a weird case because this carbon here has 6 electrons. Right? It's missing 2 electrons. It does not fulfill the octet rule. 2 electrons there, 2 electrons here, and another 2 electrons here, having 6 electrons total, right? That does not fulfill the octet rule. There's empty p orbital here, which I'm going to draw out like this, right? Where that carbon is missing electrons. Now, when I bring in the alkene that we have from the reactant here, like that, one of the carbons of the alkene here, let's say this one here, attacks that empty p orbital, right, making a bond between this carbon and that carbon right there. At the same time, as this carbon here is gaining electrons, right, it's becoming more nucleophilic, right, as it's gaining electrons. Whereas this alkene here is losing electrons, making it more electrophilic. So at the same time, this carbon here that is being attacked is going to use its pair of electrons to attack the other carbon of the alkene at the same time. So whenever you see a carbene here, which is like a neutral carbon with 2 bonds and a pair of electrons, think of that as like the nucleophile and electrophile at the same time. It's acting both as a nucleophile and electrophile, right? Same as this alkene. A logical way that you can think about it is that one carbon of the alkene here attacks the empty p orbital of that carbon, and then at the same time, that carbon attacks the other end of the alkene using its pair of electrons. And because it's happening at the same time, simultaneously, they have to attack on the same face, right? Like if this bond here is going to be a wedge, this bond here would also have to be a wedge, like that. So let's say that we draw in our products in like this. If I have a wedge bond there, this bond would also have to be a wedge, the same side, because these 2 bonds here are being formed at the same time at the same face, right? Which would force like the hydrogens here to be dashes, right? Instead of being a wedge, it could have been dashes as well. And since this is the only center that will change, then we could use this plus minus symbol to show that we could have formed the enantiomers as well. Does that mechanism make sense on like how we need to put stereochemistry here and why there are both wedges or both dashes?
Yeah, that makes a lot more sense. Thank you.
Yeah, of course. And if this was not a chiral center, right? Like let's say there were 2 methyls here, then we did not have to put wedges or dashes at all because this would no longer be a chiral center. That would no longer be chiral center. So we don't need to put wedge or dash anymore, right? That's good. Okay. Right, let me import this document in so then we can look through this mechanism here that you say I tried, and then I'll check the work at the same time. Let's go here, right there, share, add, it's good. Okay, share screen. Yeah, and also I formed this chart recently with the different alkene reactions like hydrogenation and all the electrophilic addition reactions, the reagents you see for those reactions, the regioselectivity of them, like if it's Markovnikov, anti-Markovnikov, or if there's none, stereoselectivity of them is like syn addition, anti-addition, or if there's none, based on the intermediate carbocation or radical intermediate. And then the yellow stars here are the ones that you have to know the mechanisms for sure, right? The ones that I did not star in yellow, I would not worry about that mechanism, because that's less likely to show up on the test. And before, when I like was tutoring in person at Davis, I made like note cards for the Helix class. But this was the pen and paper one before I moved on to the iPad note card, right? Where this is like the front face of the flashcard, and this is the back side of the flashcard right there, with all the mechanisms and reactions that you need to know for the first midterm for Helix, right? And this mass spectrometry notes here as well, which is going to show up as conceptual questions, multiple choice, right? So mass spectrometry is just going to be an explanation or multiple choice, most likely multiple choice question, which is explained there. And then if we have time, we'll do like alkene synthesis problems. But for now, let's just go over the homework. Oh yeah, and also like the previous midterms from Helix as well, midterm 1 from winter 2023. Yeah, this is winter 2023. I think you guys have the 2024 one on Canvas. This is the 2023 one. Right. Yeah, 2023. Okay.
Where is all of this?
All of this will be posted on the school website, like on the classroom with the recording and notes for these office hours, like all these resources.
Perfect. Thank you.
Yeah. Okay. And there's also going to be a midterm 1 review session next Monday from 9 to 11 p.m. So it's like basically office hours, but extended to 2 hours for Win 19B exclusively next Monday. Okay. So, Elysia, when you drew out this mechanism right here, don't forget the negative charge on this carbon and the positive charge on this nitrogen right here, right? Because if this was a mechanism type problem, those formal charges are very important.
Yeah, I really saw that. I just didn't know if it was
Yeah. Right. Like when you see these right here, make sure to like count the formal charges. Like, were these shown in like your notes as well, lecture slides as well for Helix, or?
Yeah, he had us, or is it him? Or no, I don't know, not Felix, but Edna.
Oh, right. Yeah. Edna, yeah.
I knew it was, there were charges there. I didn't know if I was supposed to include it or not.
Yeah, it's okay. If this was not predicted product, you don't have to worry about it. But for formal charge, it would be like graded for mechanism type of problem. Yeah. That's good. So for the second mechanism right here with the CHCl3 turbutoxide, we have a strong base turbutoxide right here. That's gonna deprotonate this CHCl3 acid, where this is the acid, this is the base. Once we do that, right, we have a negative charge on this carbon. And we have one of the good leaving groups, chlorine here, it's just going to leave by itself, right? Because this is so unstable right now. One of the bonds here is just going to kick out a chlorine to give us this carbene right here. And it's very similar to the last example we did. This carbon here is going to be a nucleophile and electrophile at the same time, right? Because it has an empty p orbital, since it is missing 2 electrons. And the alkene here is going to attack that carbon, and at the same time, that carbon is going to attack the other end of the alkene, forming this bond right here, right? And because if it's attacked at the same time, those bonds would be on the same side. They both would have been wedges or dashes. And since these are the only 2 enantiomers we have, I mean, chiral centers we have, we could say plus or minus symbol right there. That's good.
One thing that I was saying that kind of helped me understand it was like she was saying that after like the was attacking, then carbon is left with a negative charge, and carbon was like, I don't want to be negative, so then the point is like, I'll take it. That's when the point is.
Oh yeah, like this intermediate here, like is very unstable. This carbon here is like, I don't want to be negative. And then chlorine is like, yeah, it will take it because it is more electronegative. Yeah. Right. Because this chlorine negative charge here can handle that negative charge because that chlorine is highly electronegative. Yeah, that's good.
Hello.
Hello.
Brian, how can you make a cyclopropane so easily that it's highly unstable due to angle strain?
This structure here.
No, in first question.
First question. This one right here.
Yeah, cyclopropane can't be made so easily due to angle strain.
Yeah, so this cyclopropane here is unstable because of angle strain,
Yeah.
but that is just like a product that can be formed, but it is an extremely unstable product because of that high angle strain.
So the reaction is reversible. You are saying that?
Yes, you can actually open up this ring. And do you know what kind of reagent can open up the ring?
No, I don't really know.
Uh-huh. It would be like H2 PDC, right? When you put H2 in metal catalyst, that would open up the ring. If you have a cyclopropane or cyclobutane, those rings with high ring strain, like you said, are extremely unstable. We can actually open them up with H2 PDC. H2 PDC, which is going to open up the ring into alkanes like that, right? But we can actually form cyclopropanes from this reaction here with alkene. But like you said, this is highly ring strained, highly unstable, but it can still be formed.
Okay.
Yeah. Nice. Okay. So the next one here, this mechanism, zinc metal catalyst, is going to attack that carbon. And then eventually form this carbene right here, which is going to do the same exact mechanism for like the first reaction we did, forming that cyclopropane right here. And if you drew out this hydrogen right here, and you drew out those bonds right there, make sure to draw H's here explicitly like that, because those look like methyl groups right now. Right. And then this right here, this reaction with the zinc and iodine catalyst, that's called the Simmons-Smith reaction, I think. Yeah, so you might see that like written out, Simmons-Smith reaction. Right. Yeah, Simmons-Smith reagent. Right, this right here is the Simmons-Smith reagent. Right. Okay. So number 2, let me check your guys' work here. Oh shoot, did you skip over number 2, Elysia?
Yeah,
That's okay, it's okay.
there's like radical hallucination and
Yeah, so let me check Layla's number 2. You attacked the bromine with 1 carbon, attacking the other side, kicking out that leaving group, forming the bromonium ion, correct? And then you use the water to attack the more subside, that's correct, kicking out the leaving group. Then you deprotonate it to make it neutral, yes. And you have that base. Okay, so the last part is when you had the questions on like the last part of that intermediate, Layla.
Yeah.
Yeah. Okay, so let me show you guys this mechanism here. Okay. Yeah. Right. So number 2, BR, attack that bromine, kick out the other bromine, and then the bromine being attacked is going to attack the other alkene carbon at the same time, forming this bromonium ion intermediate here. Where that bromine is going to have a positive charge, and I'm going to make this methyl on this carbon here a dash, right? Because wait, actually 1, 2, 3. We don't actually have to do that. Nope, it could actually still be planar. Because the dash thing here... Well, actually, no, never mind. We do actually have to do that. There's 4 bonds there. Great. This carbon here will have 2 flat bonds, 1 wedge, 1 dash. And I'm making the dash bond here that methyl group. Right. Now, we have a competition between nucleophiles. Br minus versus water. And you chose the correct nucleophile, the water, because there's a million times more water than Br minus, which is going to attack the more subside, popping up the bromonium ion, doing backside attack, inverting stereochemistry, and leading to this intermediate here. Right, so this is going to be a dashed oxonium ion with a positive charge, forcing that methyl group to be a wedge now. Now, the other step is going to bring in another water or Br minus to deprotonate and neutralize that oxonium ion to get neutral OH, alcohol. Like this, okay? Now, that's the end of the first step. If you just have Br2 with water, this would be the final answer, plus minus, right, in enantiomer. But now, when we bring in the strong base, bulky base right here, we're gonna look for the most acidic hydrogen. What hydrogen would you guys say is the most acidic hydrogen that's gonna get deprotonated here from this molecule, that intermediate? What's the most acidic hydrogen you guys see right now?
Next to the tertiary butyl, next to
the tertiary
Tertiary
carbon? Are you saying is this hydrogen here or is this hydrogen here?
first one.
First one. This one right here?
Yeah.
Yeah, so you're thinking of E2 reaction, right? Where you're gonna grab that hydrogen, make a double bond
Yeah.
here, and kick out the leaving group. That would be
Yeah.
E2 reaction.
Yeah.
But there is another acidic hydrogen here, right?
Of alcohol.
The alcohol hydrogen. This one right here, yes. When you see a hydrogen on an electronegative atom like oxygen, that hydrogen is going to be more acidic than the alpha hydrogen here. So we're not going to do E2 reaction. We're going to do an acid-base reaction instead. We're going to deprotonate the alcohol hydrogen. So this O minus here is going to attack that hydrogen. The bond between that hydrogen and oxygen is going to break and give that oxygen a negative charge. Right, so we're deprotonating the alcohol to make the oxonium alkoxide ion here. Like this. Br. And this is going to be O minus right here. This is now our nucleophile, the negative charge oxygen. And I'm going to star that oxygen. And we have an electrophile here, which is this carbon here. And this is our good leaving group. So we're going to do an intramolecular Williamson ether synthesis reaction here. This nucleophile is going to attack this electrophile and kick out the leaving group at the same time. SN2 reaction. It's going to do a backside attack, so we're going to invert stereochemistry here. And that's going to give us this final product here. Right. Where we formed... What functional group is this here that you guys recognize? Right.
Ether.
Ether. Yes, it is a cyclic ether, but what is the specific name of this ether? It is an ether, but this three-membered ether has a specific name.
Epoxide?
Yes, epoxide. Epoxide is a cyclic ether. Yes, cyclic ether. But this cyclic ether is specifically an epoxide. So that's one way that we can form epoxides. Right. But did this last reaction make sense? The intramolecular Williamson ether synthesis, where our nucleophile here is on the same molecule as that electrophile, and because the molecule is attacking itself, we're forming a ring here, right? All intramolecular reactions will always form a ring, and an intramolecular reaction is when we have a nucleophile on the same side as the electrophile.
Could you repeat again why it takes the hydrogen by the O instead of the other one?
Yeah. We take the hydrogen by the O instead of the other one because this hydrogen here is more acidic than this hydrogen, right? If we were to compare the stability of the conjugate base of, let's say, this negative charge, if we deprotonated that hydrogen instead, and this negative charge here on the oxygen, the negative charge on the oxygen would be more stable, right? And because it's more stable, it's going to be less reactive, And because it's less reactive, this is considered a weak conjugate base, right? This is the conjugate base of if we deprotonated the hydrogen instead, like this hydrogen on the other end, and let's say we put a negative charge right there. Whereas this is the conjugate base of if we deprotonated the alcohol, giving a negative charge on that oxygen. If we compare the stability of this negative charge versus this negative charge is more stable because it's on a more electronegative atom. And because it's more stable, it's going to be more happy, less reactive, less energy, making it a weak conjugate base. And a weak conjugate base comes from stronger acid. Right. Another way you can think about it is that when this alcohol here loses its proton, loses its hydrogen, it's happy to stay as a negative charge here. More happy than if this carbon here loses its proton and gains a negative charge, right? This carbon here is more angry because it's less electronegative than oxygen, more angry, so it wants to go back to what it was before, making it a weaker acid. This alcohol H here is a stronger acid because it can handle that negative charge and be happy with it. Right? Be stable with it, less reactive with it, with conjugate base.
Okay, thank you so much.
Yeah, nice. So let me give you another example here. If I give you this right here, and I have NaOH and water, and I draw out all of the hydrogens, which hydrogen would you say is the most acidic hydrogen that is going to get deprotonated?
Alcoholic hydrogen.
Yes. Because when we deprotonate that alcohol hydrogen, the negative charge on the oxygen is stabilized by the electronegativity of the oxygen, and it could do resonance with the carbonyl, right? Okay, so that would be number one. Now let's ignore that. Which hydrogen would be more acidic? This set of hydrogens or this set of hydrogens here? And why? Yes, these two H's here would be more acidic because if we deprotonated one of them and give that carbon a negative charge, that negative charge can do resonance with the carbonyl like that, right? Whereas if we deprotonate one of the hydrogens here and give this carbon a negative charge, this negative charge on that carbon cannot do resonance at all, right? Because this is an sp3 roadblock. It's stuck. It cannot do resonance. So this is our second most acidic hydrogen in this molecule. This is our third most acidic hydrogen in this molecule. Right. And the reason why, like, the oxygen minus is more acidic than, like, more stable than this carbon minus, both can do resonance with the carbonyl. So since both can do resonance, we ignore the resonance factor. Then we look at the induction factor. Which atom can hold that negative charge better? Which is the more electronegative oxygen atom here, compared to the less electronegative carbon atom. Right. Okay. So that's gonna be like applying to like this scenario as well. If we have a strong base here, we then look at all of the hydrogens present and choose the most acidic hydrogen present, which is this alcohol H right there, which then gives us our nucleophilic O minus, and that would do the intramolecular Williamson ether synthesis to form this ether, cyclic ether or epoxide. And this would be plus minus, right? Plus enantiomer, because these stereochemistry could have been inverted. Like this could have been wedge, and this could have been dash as well, like that. Okay. Any questions on this problem?
Can you do the same question instead of bromine water? You take HBr, so you go with mechanism like carbocation, not NCC.
Yeah. So if you bring in the same reactant, but instead of the reagents we have, and we have HBr, what do you think is gonna happen? Like, how would you describe the mechanism errors if we just have HBr? What's gonna happen? Like, what's gonna happen in the first step of the mechanism here?
Now form the carbocation.
form a
On the-
carbocation.
Yeah.
Which carbon? Let's say this carbon or this carbon.
No, first one.
The first one, this one.
Yeah.
Yeah. So when we want to form a carbocation, we want to form the more stable carbocation. Are you familiar with the stability of carbocation and like
Yeah. Yeah.
the
Yeah.
more
Yeah.
substituted it is, the more stable it is? So which carbon would you say is more substituted? Let's say this is A, this is B. Which one is more substituted, would you say?
B.
B, right. That's where we want the carbocation to be at,
Yeah.
right? But that means that this one right here is going to attack the H from the HBr, kick out the Br to give us this carbocation intermediate. Right. This carbon here is the one that attacked the hydrogen, but this carbon right here is the one that lost the bond, making it have the carbocation, the more substituted one. And whenever we form a carbocation intermediate, we always look out for any rearrangement steps, like a hydride shift or methyl shift. Do we have to do any shifts here?
No.
No, right, because it's already in its most stable position. That's right.
Yeah. Yeah.
So now, what do you think is going to happen in the next step?
I think bromine attack on this carbocation.
Bromine minus attacks that carbocation, giving you this product here. And because we have a chiral center formed, we have to put stereochemistry, right? Because this bromine here is attacking this flat sp2 carbon, it could attack on the top side, giving you a wedge bromine, or the back side, giving you a dash bromine, right? In this case, I attack the back side, giving us a dash bromine, forcing this methyl to become a wedge. I could have done the other way as well, so I'm going to put that plus minus symbol to show the enantiomer product instead of drawing up the different product, right? Okay. That's good. Let's move on to number 3. Okay. Number 3. Let's check Layla's answer. MCPBA. Yep. So when you see MCPBA and an alkene, think of forming epoxide. This is epoxide formation. When you see MCPBA, always associate that with epoxide, right? So if we form an epoxide with that alkene right there, Layla chose wedge, right? This methyl here is going to be a dash, right? So don't forget that dash as well, Layla. Like, don't keep that as a flat bond because there's a stereochemistry there now, stereocenter there now. Right. And you could have also done plus minus here as well. But for example, let's say this ethyl here was not a flat bond. Let's say it was dashed like that. And this was dashed right here. You can no longer do that symbol, plus minus symbol, right? Because the other product is not the enantiomer of this. The other product is going to be a diastereomer of that, right? Because this chiral center here stays untouched. Nothing changes that stereocenter. It stays as a dash. But the epoxide that we form here could have been a dash, making this methyl here a wedge, right? So these two chiral centers here changes, whereas this chiral center here stays the same. So these are diastereomers of each other, not enantiomers of each other. Right. Okay. Any questions on problem number 3?
So this one is non-reciproc?
This one is non-reciproc. Yeah, this is not reciproc.
And you were saying just imagine if you were to change that to a dash bond, that is why you can't say that reciproc because one is going to be a
Yeah, because when we have MCPBA right here, that's going to make an epoxide from this alkene. And when we make the epoxide, it could have been a wedge or a dash. So this is the wedge epoxide. This is the dash epoxide, right? And this is the chiral center here that gets formed. So like if the epoxide is a wedge, then this methyl has to be a dash. If the epoxide is a dash, this methyl has to be a wedge. So the chiral centers here that I'm circling are the one that changes, right? But the one that I'm pointing at here, that chiral center, stays untouched. Nothing touches that chiral center. It will stay as a dash, Right. So because that chiral center stays the same, and some chiral centers change, these are diastereomers of each other.
Okay.
Mhm.
Okay, that makes sense.
Yeah. Skip.
So it would only be plus minus if all stereocenters change, basically.
Yeah, it would be plus minus if all stereocenters change. Yeah, that's right. And keep that in mind because Helix sometimes puts like questions like this where he tries to be tricky, and a lot of people are used to putting plus minus, but you get points off for that for an example like this, right? So only put plus minus if all chiral centers change. If you see that there's one chiral center that is like not doing anything at all, not changing, then do not put that plus minus. Draw out the other product out explicitly.
And would that be the only case where like if something is like one stereocenter didn't change and the other one did, you have to indicate that line rather than assume that it's increasing?
Right. Sorry. Can you say that again? I couldn't hear you.
Oh yeah.
Uh-huh.
Oh sorry. I think I. Can you hear me better?
Yes. It's much better.
Okay. So just wanted to clarify that the way that we notice or like the way that we know that it's not racemic is if one bond or one stereocenter changes but the other one doesn't. So then that means that we have to indicate the other like the
Diastereomer.
the diastereomer.
Yeah, that's correct. And it does have to be one stereocenter that changes. It could be multiple. In this case, two chiral centers changes. These two chiral centers that I just X'd out are the ones that are changing.
Okay. Thank you.
Right. Yeah, because diastereomers, some chiral centers will change, some chiral centers will stay the same. So let's say we had 3 chiral centers in the molecule. Diastereomers would be like if 2 chiral centers change and one stays the same, like this one, diastereomers. Or it could be one chiral center changes, only one, but the other 2 stays the same. Then that's also diastereomers, right? So it's some chiral centers change, some stay the same, diastereomers. Whereas in enantiomers, this plus minus symbol is every single chiral center in the molecule would have to change, would have to invert to be considered enantiomer.
Okay, so this would be considered diastereomer.
Yeah, this right here would be considered diastereomers of each other, these 2 molecules.
Okay, thank you.
Yeah, of course. Okay, number 4. Ooh, okay. You even drew out the mechanism here.
Yeah, it's kind of long for the other one, so it's like
I know. Like dihydroxylation. He did go over it in lecture, but there's a low chance that this will show up as a mechanism problem. Like it's more likely going to be like one of the acid ones with the carbocation, and you have to do like a shift, like a hydro shift or something. Right. This one here, yeah. This one makes a vicinal syn diol where we add 2 alcohols on the same side adjacent to each other.
And the thing
good.
was, what makes that first one versus the second one is the other one is actually trans.
Yes. This one here is syn. The other one is.
I may have not indicated it though.
Trans.
But I
Yeah.
think
Yeah. You indicated it here, like wedge and dash, but then at the end, final answer, you switched it up for some reason.
yeah, I think I was just copy and pasting it.
Oh yeah. But you get the general idea though, so
Yeah.
that's good. Yeah. Let me check Layla's number 4. Oh yeah, so Layla, this right here is not ozonolysis, right? The Zizix reaction, ozonolysis, is when you see O3. This has O in it, but it's not ozonolysis. This is dihydroxylation for the first one. Right?
Oh, oops.
It's okay. Some other things I wanted to point out here is that you know how this is a chiral center?
Yes.
You did put the wedge here, that's correct, but we cannot have 3 flat bonds. You have to choose one bond that is gonna become a dash.
Oh, okay.
So you could say this is a dash, or you could say this is a dash. It's kind of hard to choose, but you could basically choose here because when this oxygen here comes to attack that alkene and this alkene attacks oxygen, it could attack either on the top side or bottom side. So it's randomized here. Like you get to choose the stereochemistry. Make sure like 2 bonds are flat, 1 bond is wedged, and 1 bond is dashed, like that.
Okay, that makes sense.
Mhm.
And you said it's because one can be hit from the front or the back.
Yeah. Right.
Uh,
Front or the back because of this sp2 flat trigonal planar carbon right there. It's not tetrahedral like SN2 where like you know exactly what the stereochemistry is like. You just invert it. This one here is actually randomized. You could attack it from the front or the back.
okay, that makes sense. Thank you.
Yeah. And also over here, you can put that methyl as a dash, or you can just leave it as a flat bond like that and put the invisible hydrogen as a dash like that. Both ways would work. But the way that you did here would also work as well.
Okay.
Yeah. Nice. Now this one right here is going to make the trans one because MCPBA, like we said, what functional group does that make?
Epoxide.
Yes, right here, epoxide. That's good. And I'm gonna put this as a dash bond like that. You chose acid, so that's gonna protonate the epoxide oxygen, creating this good leaving group right here. Right. Now, once we have that good leaving group, if this was a mechanism problem, in acidic conditions, where would the water want to attack? The more subside or the less subside? In acidic conditions, when we opening up epoxides in acidic conditions.
Isn't it the left subside?
That's gonna be basic conditions. Basic conditions would want to open up on the left subside, but the final answer doesn't really matter because you get alcohol on both sides anyway. But if in the mechanism, like if he wants you to draw it out, this right here would be wrong because the water would not want to attack the left subside in acidic conditions.
Oh.
Right. And the reason why, instead of memorizing it, and you want to understand why it attacks the more subside, is because think of this as the good leaving group, right? Do we want to make the carbocation on the more subside or the less subside?
The more.
Yeah, the more subside. So the leaving group here is actually going to leave on the more subside, which is why the water prefers to attack that more subside to go through the more stable carbocation intermediate, right? In acidic conditions. Right. Okay. So when this water here attacks the more subside, kick out the leaving group, invert stereochemistry. This would be dash OH2 plus, and this would be the wedged OH. And then we use this water to deprotonate one of the H's to give us like that anti dihydroxy product right there. Right. So your answer is basically correct. Like it's anti to each other, but the mechanism here, if it shows up, make sure if you choose acidic conditions or if you see acidic conditions, the nucleophile will attack the more subside because that goes through the more stable carbocation intermediate.
And we say that we know the more acidic because of the carbocation that is there?
Yeah, because well, we don't actually form the carbocation intermediate. We just say that, let's say I have something like this, and I have this epoxide right here that is protonated with the positive charge, and I have, let's say, CH3, CH2, OH as a nucleophile. Just imagine that this is the good leaving group, and if we pop up the leaving group away like that, a carbocation is going to form here. If we pop up the leaving group away like that, a positive charge is going to be here. We know that the positive charge is more stable at the more subside, so there is a bigger positive charge residing or living in the more sub carbon right here because it's more stable there. And because there's a bigger positive charge on the more subside right there, the nucleophile here is going to attack that more subside. Right. And we know that this is in acidic conditions because this epoxide is protonated with a positive charge.
Okay, that makes sense.
And when we attack that more subside, we're going to invert the stereochemistry like from a wedge to a dash like that.
And was that what you were indicating on the other one?
Yes, that's what I was indicating in the other one, because if I finish this out,
Oh, that was a dash,
yeah,
not a wedge.
wait, where this is the dash right here. That was what I was indicating, right? Where when this water here attacks that carbon and we kick out the leaving group, this wedge inverts into a dash right there.
And what does the other arrow tell you? The one right next to it?
Oh, this one right here?
Oh yeah, from the like OH2, you moved
Uh-huh.
it to the other one.
Yes, I moved the OH2 to this one because the OH2 here attacked the more sub side, so that's why it should be on the more sub carbon. This OH2 right here. And this
Okay.
is a neutral OH, which is the neutral OH from the epoxide OH right there. That
So
stays
then
as a wedge.
There's no carbocation or like charge. Sorry.
Yeah, there's no charge on this carbon, right? No charge on that carbon. Before, it had a positive charge on that oxygen, right? But when we attack that carbon and we break this bond and kick it onto that oxygen right there, this oxygen gains 2 electrons from that bond, making it neutral, like that.
Okay.
Yeah.
That makes sense. Thank you.
Yeah. Yeah. So if I finish this out, this would be dashed O, CH2, CH3, H plus. The methyl would be a wedge now. And this right here is supposed to be a wedged OH, but I'm going to make it flat and planar. The reason why it's flat and planar is because this is not a chiral center. There's 2 hydrogens right there. Right. And then we could just finish this off by deprotonating the oxygen and making it neutral. Right. Like that. Plus minus. Right. Okay. In basic conditions, like let's say we did have basic conditions, like the same epoxide right here. And we have CH3, CH2O minus, then we don't think about carbocation or where the positive charge is more stable at now. We think of steric hindrance. In SN2, where would the nucleophile want to attack? The more subcarbon or the less subcarbon? More sterically hindered carbon or less sterically hindered carbon? For SN2 reactions.
Well, for SN2, the least substituted, right?
Yeah, the least substituted one, because there's more space there. There's less crowd. There's less groups there, allowing for the nucleophile to attack that substrate for SN2. Popping the double bond onto the oxygen right there and giving us this intermediate right here. There is no wedge dasher because this is not a chiral center. If this was a chiral center, we would have to put that as a dash, right? Because we invert stereochemistry here. We invert this wedge into a dash, but I'm not drawing a dash there because this is not a chiral center. And then the last step here, we're just to protonate this O minus with the solvent or acid workup. Let's say we have the solvent. It's just gonna grab that hydrogen and become neutral. OH, like that. Right, so that's the differences between acidic versus basic conditions in opening up epoxides. In acidic conditions, we attack the more subside because the positive charge is more stable there. In basic conditions, we attack the less subside because there's more space there, less steric hindrance there.
Okay, that makes sense.
Yeah. Okay. Now let's do number 5, which is the Zizzers reaction, ozone-analysis. Layla, did you try out the number 5? I don't see it here that you sent me.
No, I skipped that one because it would confuse me.
Like you didn't recognize the reagents O3s.
No,
CH3s.
I recognized the fact that it was an ozone-analysis, but I just couldn't figure out how like it would break in so many different ways.
Yeah. to do that, how did you think about this, Elysia? What was your thought process on this problem?
Yeah, so what Brian was saying was like every time that you see a double bond, you just like draw like a line right down the middle and like cut it. So like you like grab your scissors and cut it, and then you basically pull those apart, and between those two carbons, it still has those double bonds, but you attach an oxygen to it. So that's why there's like in like 3 different spots you have like 2 oxygens between each one that you kind of cut, because there are the 2 protons between.
Yeah.
Two electrons. Sorry.
2 the electrons, where when you cut the double bond in half, put oxygens in the middle like that, and that would be your final product, right? Because this is the cut between them. Like there used to be a double bond there, but we made that cut and we just put oxygens in the middle like that. That's the cut right there. Oxygens in the middle like that. Cut right there. Oxygens in the middle like that. So you could just leave your final answer like this. You don't have to like draw it out into like the neat bond line form. You can leave it like this and you get full credit still as that answer.
Bro, it's oxidative ozonolysis, right?
Yes.
Can you do reductive?
Reductive, like converting these
Reductive
carbonyls.
ozonolysis.
Reductive ozonolysis.
Yeah.
Let me see. I have not heard about that before. Let me see what that is actually. Reductive ozonolysis.
In which you take, instead of dimethyl ether, thioether, instead of you take H2O2.
That's very good. Reductive. Okay. Yeah, so this is reductive ozonolysis. The first step is ozonolysis. The second step is reduction, reducing agent.
Yeah.
Right. So this right here is reductive ozonolysis. Like, what is oxidative ozonolysis? Oxidative ozonolysis. Yeah, so they're like the same thing. Like when we do ozonolysis, we just cut up the double bond like that. There's no like reductive versus ozonolysis, oxidative ozonolysis. There's just one type of ozonolysis, right? Which is reductive ozonolysis, like you said. First step O3. Second step is a reducing agent. Right here. This right here.
No, there is oxidative, in which you form, instead of ketone, you form carboxylic acid.
Carboxylic acid. Oh, that you're talking about the K-104 one. That's that's not gonna be ozonolysis. That's permanganate. That's a different reaction. Right? Yeah. So let me show you that instead. That reaction right here. So that is this reaction here. Permanganate. So if we have the same alkene like this, and we react it with these reagents, KMnO4, liquid, NaOH, water, we are going to do the same exact thing as ozonolysis, right? Cut the double bonds in half, but we're going
Take acidic KMnO4, not NaOH water. Take hot KMnO4.
Wait, what? Sorry?
Hot KMnO4.
Hot KMnO4. Yeah. So this will be done with heat or room temperature. So you can see that delta symbol, heat, to show the hot conditions, or room temperature. And that's gonna do the same exact thing as ozonolysis. You're gonna make carbonyl, but you cannot stop at the aldehyde. Whenever you have an aldehyde, you go all the way to the carboxylic acid, right? You can't stop at the ketone because we can't oxidize the ketone further. So this is gonna be one of the products here. That's a ketone. But this aldehyde right here is gonna be further oxidized to the carboxylic acid. We're gonna oxidize that further to carboxylic acid. Same as for this aldehyde right here. That's gonna be oxidized further into the carboxylic acid, and this aldehyde right here as well, and this formaldehyde right here is going to
correct
go to this formic acid right there, like that.
Yeah.
Right. So this is not ozonolysis. This is potassium permanganate oxidation, right? Ozonolysis is the one with the O3. It does a very similar reaction as ozonolysis, but it is stronger than ozonolysis. It's going to oxidize all the aldehydes into carboxylic acids. So that is that reaction right there. Yeah. Nice. But for Helix's class, don't worry about this reaction because he did not go over this reaction. This is a different reaction, right? Which is a stronger ozonolysis reaction here. You don't stop at the aldehyde. You're going to go all the way to carboxylic acids. All your aldehydes will convert into carboxylic acids. Yeah. Any questions on that, Rohan? Or anything else?
No.
Yeah.
No.
That's good. Okay. So let's move on to number 6. Stereo. Okay.
That
So
one submit on a, oh sorry.
Oh yeah, you just submitted that right now on Discord.
On Discord, but it's just a screenshot.
Oh yeah, I see it. So you put.
I'm not sure if it's correct though.
Let's see.
I didn't do the mechanism.
Okay, so let's think about the first one here, HBr. What would HBr do to this alkene? Let's think about this mechanistic. What's the first step here? HBr and this alkene right here.
I say that the alkene grabs the bromine and then the arrow draws towards the hydrogen and leaves it.
Does not grab the bromine. The hydrogen, kick out the bromine and form a carbocation. And we want to form the more substituted carbocation, which is going to be this right here. Now, after we get that carbocation intermediate, what's going to happen next right here?
I don't know.
So whenever we have this carbocation intermediate, we stop, look out for any shifts that we can do. Because this is already in its most stable position, we don't have to do any hydride shift or metal shift. Right. Then we bring in the Br minus to attack that carbocation. So this is the previous reaction we did, the hydrohalogenation reaction, right? Where the Br minus that got kicked out is going to come back and attack that carbocation to form this product here. Where, because it can attack on the top side or bottom side, the bromine could be a wedge or dash. Let's say it's a wedge, that's going to force the methyl to become a dash. And because this is the only chiral center here that changes, we could do that plus minus symbol, plus enantiomer. Okay. Did that make sense, Elysia?
Yeah, I think so.
Yeah, so that is like the, what reaction was it? Yeah, like this reaction we did earlier, addition of HX or hydrohalogenation, protonate the alkene, make the more stable carbocation intermediate, stop, look for any shifts that you could do, hydride or metal shift, and then once you get the most stable carbocation intermediate, the X minus that got kicked out is going to attack the carbocation to give you your final product, like that.
Bro, why didn't you rearrange the carbocation?
Why didn't I sorry, what was that?
Why didn't you rearrange the rearrangement
for this
in this
intermediate
question?
Here?
Yes,
I did not rearrange because this is the tertiary carbocation, the most substituted carbocation.
No, but it has only 5 alpha H, na?
5
alpha hydrogen. When it rearrange, it will get 6 alpha hydrogen.
Five hydrogens, or like, are you talking about this carbon right here?
Yeah.
This
now
carbon.
Now this carbocation shift with the next two carbon.
Oh, this one right here.
Yeah.
So if it shifts over here, that would also be a tertiary carbocation, but it's already a tertiary carbocation. Like if you look at this carbon right here in pink, that carbon is attached to 3 other carbons already. 1, 2, 3. If you
this isn't how we see this. You know hyperconjugation?
Yes.
Then in this you count alpha hydrogen. More is the alpha hydrogen, more is the stability. Do you know alpha hydrogens?
Alpha hydrogens. Yes.
So here carbocation has only 5 alpha hydrogen, but when it rearranges, it will get 6 alpha hydrogen. Shift the methyl to the carbocation and the carbocation to the next. Yeah.
Oh, I see what you're doing. Methyl shift here, and then
Yeah.
have this right here. Two,
Yeah.
three, positive charge. Oh, and then there's 6 alpha hydrogens right here. 1, 2, 3, 4, 5, 6
Yeah.
alpha hydrogens. Okay. Yeah. So, okay. So, if that's
Isn't this correct?
yeah, that's gonna be more hyperconjugation.
So
yeah,
more stable.
Yeah, more stable. Right. But for 118A or 118B, we wouldn't have to worry about that. So yeah, this would be more stable because of more alpha hydrogens. 1, 2, 3, 4, 5, 6 alpha hydrogens. Whereas this one here is gonna have 1, 2, 3, 4, 5 alpha hydrogens. Yeah. But wouldn't the methyl groups here also do hyperconjugation because there's a bigger R group here? Or does it matter like about the alpha hydrogens? Because this is the equal amount of substitutions as well. So I wouldn't say that this is more stable or this is more stable. You could actually do both and say that they're both equally stable, right?
Okay.
But this methyl shift here is going to require more work for the carbocation, and the examples that I've seen does not do this shift right here, right? So yeah, you can say this works as well, but the examples that I've seen does not do that because this methyl shift here requires more energy, which is going to make it less yield. So when the bromine minus attacks that carbocation, it could attack on the top side, giving us a wedge product, or the back side, giving us a dash product plus enantiomer like that. Right. And for Layla, you put the bromine on the right spot, but don't forget your wedges and dashes, Layla, because that's a chiral center right there. For Levin's class, that counts as both wedge or dash, but for Helix, he wants you to draw out that wedge or dash out explicitly and show plus or minus, Layla.
Okay, I keep forgetting like when to use it.
Yeah,
But,
you use it when
yeah.
you see a chiral center, right? Like this right here is a chiral center, so that's when you use it.
Okay.
Yeah. And for the next reaction, HBr, roar, and heat, when you see
I
peroxide
messed that up.
right here,
Oh wait, no.
yeah, you got it correct. You put bromine on the anti-Markovnikov position, right? The Lessa position, where you put bromine at the Lessa position right there, like that, right? But you notice how we have two chiral centers here, one here and another one here. For Helix's class, we would want to put stereochemistry, but this one here right here is going to get a little bit tricky because the intermediate that this goes through when you see roar is a radical intermediate, right? With all the initiation, propagation, termination steps. And when you form radicals, think of it like as the carbocation, it's flat and planar. So I'm going to draw out the products here and go over the mechanism for tomorrow, but these are the different products you could get here. You could get a wedge methyl there, a wedge bromine here, plus minus that, or you can have dash methyl there, wedged bromine here, plus minus that, or you can have yeah, those are the two you could have. I was gonna say wedge methyl here and dash bromine here, but that's the enantiomer of this. Of this right here. Right, yeah. So we get 4 different products here. This set of enantiomers and this set of enantiomers right here. Right. The reason why we get like randomized stereochemistry here is because of the radical intermediate that it goes through. And you're gonna see that clearly with the mechanism initiation, propagation, termination step here. But the regional selectivity, bromine is gonna attach to the less subside, antimark side, like that. Right. So the differences between these two reactions here, HBr at the top is going to attach bromine to the Markovnikov side, more substituted side. The bottom one here with the peroxide, roar, is going to attach bromine to the less subside, anti-Markovnikov side. Right. Any questions on number 6?
No.
Yeah. So let's see. That's good. So that was the homework problem. I posted the 2023 practice exams for you guys to try out. I'll post this to the school, and then store the ones that you guys don't know or have struggle with, and then I'll check it tomorrow with the mass spec as well. Yeah. Mhm. Yeah.
Okay, and then you said when were you gonna post them?
I'm gonna post them right now, after the office hours ends.
Oh, okay.
Uh-huh. Yeah.
Thank you so much, Brian.
Yeah, of course, Elisa.
Those homework problems actually did help with the
Uh-huh. Like understanding like the reactions and reinforcing it more.
yeah, they're actually pretty good practice.
That's good. That's good. Do more like the AETC practice, I would say, and then tomorrow, when we do more practice, I'm gonna like make synthesis problems for us to go through, and then give you more homework for tomorrow's office hours as well.
Yay, okay.
Yeah.
Thank you.
Yeah, of course.
I low-key don't know how to use school, so where do I find them?
Yeah.
Honestly.
If you're on the school website,
Uh-huh.
go to the classroom tab, and then go to the winter 2025 quarter, the currently ongoing one, and go to my office hours, week three, and then all the notes and recordings are gonna be there. So you can see the recording of this and the notes of this posted soon. The notes are gonna be there like right after this.
Wait, sorry, you said oh wait, sorry, I like don't know
Yeah.
how to use the app.
Yeah,
So
it's
I
okay.
click on your profile.
Oh, it's gonna be on the community. So it's on the community like that I'm in, the Bright Oakham Tutoring Services. And are you using your phone or the website?
I'm on my phone.
On your phone? Okay, so let me see what that looks like on my phone. Great. Are you on
Oh,
this
I
page
see
right here?
community. Yeah.
Yes,
Yeah.
Click that one. Click the classroom tab.
Classroom.
Yep. And you see the winter 2025
Winter
module?
24. Yeah.
Yeah,
Yeah.
that one. And then Brian's office hours, week 3.
Gotcha.
Yeah.
Okay, thank you so much.
Yeah. Nice. Okay.
Have a good day. Good
Yep.
night.
Good night, guys. Have a nice night.
Bye, Brian. Thank you.
Yeah. Bye, Alicia. Good
Bye,
night.
Brian.
Bye, Rohan.
It's a good day. I
Yes.
learned many things.
That's all good. What time is it for you right now over there?
Yeah.
What time is it for you right now?
What time for me? It's 11:30 a.m.
Oh, 11 a.m. I see. It's like
Yeah.
10 p.m. over here for me.
Oh.
That's good. Yeah. Well, I'll see you next office hours, Rohan.
Yeah.
Yeah. Bye.
Thank you for giving me chance.
Yeah, of course. Yeah.
Okay, bye.
Yeah. See ya.